Welcome everyone. Today we are going to start discussing about the energy stored in a stretch elastic material. The stretch elastic material that we are talking about can be a spring or any other elastic material. What I want to emphasize here, the energy stored in an elastic material is in a form of potential energy, and sometimes they can ask you the work done or the strain energy. It is the same energy that we are talking about, so do not get confused. I repeat myself. Work done, energy stored in an elastic material, or the strain energy is still talking about the same energy. So what is strain energy? Strain energy is defined as the energy stored in an elastic material during deformation when a load is applied to the elastic material. So how do we find the energy stored in an elastic material? If we consider this first diagram here, we have force against extension. So the energy is the same as the work done, and we calculate the work done as the area under the graph. So if I should shade this area, it looks like a triangle. So which means the energy or the work done will be given by the area of a triangle. Now let me try to extract the triangle out. We'll have something like this. This is the extension and this is the force. Okay, so what is the area of a triangle, which is going to give us the energy? Therefore, the energy stored in stretching an elastic material is half F times E. So we'll have energy is equal to half Fe. All right. This is the formula for energy stored in stretching an elastic material. But we know that from Hooke's law, using F is equal to Ke, it means that instead of F, I can replace Ke. All right. Then if we have E equals to half Fe, and E will be equal to half, force is what? Ke, then multiply by E, we will have E is equal to half Ke squared, because E times E will be E squared. So this can be another formula to find the energy stored in stretching an elastic material. So when given a single force and an extension, we can either use energy is equal to half Fe, or energy is equal to half Ke squared. Moving on, if we have another situation where an elastic material is extended from E1 to E2, and therefore there will be difference in forces. Okay, we have F1 and F2. Here again, if we should find the energy that is stored in stretching the elastic material, we're going to use the area under the graph. And the area under the graph will be the shaded portion. So it looks like a trapezium. And that is why if we want to find the energy stored in stretching the elastic material from E1 to E2, we will use the formula for the area of a trapezium. So if I want to extract that shape of a trapezium here, we're going to have something like this. This side will be F1. This side will be F2. And this side will be the difference in the extension. So that will be E2 minus E1. Okay? It can also be said that this side is A, this side is B, and this side is H in mathematics. So therefore, if the energy is equal to the area of a trapezium, and we know that the area of a trapezium is half A plus B H, so E will be equal to half A is F1 plus B is F2 multiplied by H is E2 minus E1. Therefore, the energy will be half sum of the forces F1 plus F2 multiplied by the difference in the extensions. So this is the formula that we can use when we are given different forces and extensions and we are instructed to calculate the energy stored in stretching the elastic material from one extension to another. Alternatively, if at all we want to use the elastic constant or the force constant, then the formula will be E is equal to half K into E2 squared minus E1 squared. Okay? Remember, if we want to find K in a situation like this, the K, which is the elastic constant, is the gradient. Okay? And how do we find the gradient? The gradient K is going to be F2 minus F1 all over E2 minus E1. So we can now move on to solve problems related to the energy stored in an elastic material when stretched. Okay, so we have a problem here and it asks us to determine the energy stored in stretching the elastic material. So what is the energy that is stored when stretching the elastic material with a force of 40 newtons and an extension of 0.08 meters? To do that, we can use one of the formulas, which is energy is equal to half Fe. So that will be half, the force is 40 newtons multiplied by the extension is 0.08. So when we do that calculation, we're going to have 1.6 joules as the answer. Alternatively, if at all we want to use the force constant, using F is equal to KE, we know that K is equal to F over E, and therefore K is equal to, the force is 40 divided by the extension is 0.08. Therefore, K is equal to 500 newtons per meter. All right, so using E is equal to half KE squared, then we will say E equals to half K is 500 multiplied by the extension is 0.08 squared. When we do the math, we will have 1.6 joules as well. All right, whether you use E equals to half KE squared or E is equal to half Fe, we will have the same answer. Moving on to the second question. It says, determine the energy stored in the elastic material when extended from 0.06 meters to 0.09 meters. We have already discussed that we can use the formula E is equal to half sum of the forces F1 plus F2 and multiply by the difference of the extension E2 minus E1. So that will be half. The force F1 is 24, F2 is 36, E2 is 0.09 minus E1 is 0.06. So that will be half multiplied by 24 plus 36 gives 60, then multiply by 0.09 minus 0.06 gives 0.03. So that will give me 0.9 joules as an answer. If I want to use the order formula again, that will be E is equal to half K E2 squared minus E1 squared. But first we need to determine K, right? And we said that K is equal to the gradient. So, and how do we find the gradient? Is the delta F divided by the delta E. That is F2 minus F1 all over E2 minus E1. So what is F2? F2 is 36 minus F1 is 24 divided by E2 is 0.09 minus E1 is 0.06. So that will be 36 minus 24 gives 12 all over 0.09 minus 0.06 gives 0.03. So 12 divided by 0.03 is 400. That will be newtons per meter. Again, going back to the formula, E is equal to half K E2 squared minus E1 squared. That will be half. K is 400 into E2 is 0.09. That will be squared minus 0.06 squared. So when we do that, we'll have half multiplied by 400 multiplied by 0.09 squared is 8.1 times 10 to the power negative 3 minus 0.06 squared is 3.6 times 10 to the power negative 3. So that will be half of 400 is 200. So that will be 200 into 8.1 times 10 to the power negative 3 minus 3.6 times 10 to the power negative 3. We will have 4.5 times 10 to the power negative 3. So if we multiply that by 200, we will still have 0.9 joules as the final answer. Thank you very much for listening to our video. If this is the first time of visiting this channel, please like, subscribe, and share the video. You can also follow us on our Facebook page.